The next talk is going to be given by Francois LeGall from Kyoto University, and he's going to tell us about the quantum advantage for the local model in distributed computing.
Okay, thank you. So I will talk about quantum distributed algorithms. And for classical computational problems, this means problems with classical inputs and outputs, this has been mostly studied in the framework of two-party communication complexity. There are a few works focusing on more than two parties. So for example, for leader election on anonymous networks, Tani, Kobayashi, and Moto proposed exact quantum algorithms. So classically, it's known that you cannot do it exactly. You need randomized classical algorithm to solve this problem. So on non-anonymous networks, there are a few prior works, but they essentially show negative results. They show that for many important problems in distributed computing, like computing the shortest passes or the minimum spanning tree, quantum computation does not help. So you can ask really over a non-anonymous network whether quantum distributed algorithm can be useful or not. And I've been working on that question for a couple of years. So the point is that there are two main models in distributed computing. So I will explain the models in the next slides. The main difference is the first model, we have limited bandwidth, and the second model, unlimited bandwidth. And for the first model, the congest model, I have shown with Frédéric Magnès last year that quantum distributed algorithm may be more powerful than classical algorithms. And in this work, we reach a similar conclusion for the local model. So I will start by describing the model and start by describing it in the classical setting. So we consider the most basic setting, non-faulty, non-anonymous, and a synchronous model. So you have a network of n nodes represented by a graph. So each node represents a processor, each edge represents a classical channel. And we suppose that each node knows only, or it knows the total number of nodes n, but except that it knows only the local topology. So for example, node 4 knows that it is connected to 1, to 3, to 6, so it knows a list of its neighbors, but nothing else. And we suppose that communication is synchronous. So communication arrives round by round, and at each round, each node can send a message to its neighbors. So for example, first round, so node 1 will send one message to 2, one message to 3, one message to 4. The contents of the message may be different. And the same for all the other nodes. And after round 1, all the nodes will perform local computations. There is no limitation. They can spend 1 minute, 1 hour, 1 week, we don't care. And then there will be a second round of communication. And again, local computation, and again, communication. And we are mostly interested in the number of rounds used to compute a function. And an important parameter is the size of the message. And there are essentially two models. The first model, congest model, we only allow short messages. So each message should be of length only, say, big of log n bits. Why log n? Because it's exactly what you need to send one ID. There are n nodes, so encoding an ID can be done in log n bits. And in the local model, there is no restriction on the size of each message. So both models have important practical motivations. The congest model is fairly close to communication complexity. The local models work well for situations where communication is very fast or very cheap. And really what you care about is purely the number of rounds needed to reach a conclusion. And I can say that the local model is really the main model in classical distributed computing. So now, quantum version is very easy. You assume there is no prior entanglement, and the only difference now is that you can send qubits instead of bits. So this means that each node is now a quantum processor, each edge is a quantum channel, and your messages consist of qubits. Okay? And there are, again, two possible models that you can define. The congest model, when you allow only short quantum message, log n quantum bits, and the local model, where there is no restriction on the size of each message. And in this prior work, we showed that there exists a problem, a fairly important problem in distributed computation called, corresponding to computing the diameter of the network that can be computed more efficiently quantumly. So more precisely, in the quantum congest model, where you are able to send quantum message, you can do it in square root n rounds, where n is the number of nodes. While classically, you need a linear number of rounds, even when the diameter is constant. So this gives you a quadratic gap between the power of a classical and quantum algorithm for that problem. Okay. So this is a gap, but it's not so surprising because we already know many gaps between classical and quantum communication complexity. But what about the local model? So you see the situation is much more delicate here because what you need to compare is an unbounded amount of quantum communication and an unbounded amount of classical communication. And indeed, there was only one prior work on the quantum version of this model by Gavuel et al. So they showed that there exists a computational problem that can be solved classically, quantumly with one round, and classically requires two rounds. Okay? And in their paper, they say that this factor 2 seems to be a natural limit. But what we show in this work is that you can do much better. So we show that there exists another computational problem that can be solved in two runs in the quantum local model, but requires a linear number of rounds, classical. So this gives you a much larger separation between the computational powers of these two models, classical and quantum version of the local model. Okay. So I will now explain the details. So our separation is based on a construction from Barrett, Caves, Eastin, Elliott, Pironio, and maybe a few may know this because it has also been used in some recent results on quantum shallow circuits, in particular the result by Bravig, Osset, and Koenig. So this is this construction. So you consider a ring of n nodes. N is a multiple of 3. So you can see your ring as a triangle. So here I represent n equal 18. So in the triangle, each of the side has n over 3 nodes. And the computational problem is defined as follows. So each corner receives a bit as input. So we have 3 corners, so 3 bits, B1 given here, B2 given here, B3 given here. And each node will output 1 bit. Okay? So each of the 18 nodes here should output 1 bit. And I will now define 4 bits. Okay? 4 bits on the outputs. So MR is a parity of the bits on the right side with even index. So Z2, Z4, Z6 in this case with n is equal to 18. MB, B is for bottom, is a sum of, the parity of the bits with even index again. And L for left is the parity of the bits with even index on the left side. And odd is the parity of all the other bits. That is the bits with node index. And now I can give the first claim. So the first claim is that there exists a 2-round quantum algorithm that samples from the uniform distribution over all binary strings satisfying this condition. What does it mean? That means that if you look at the output, all the bits output by this quantum distributed algorithm on this ring, then this corresponds to sample from the uniform distribution over all the strings satisfying the condition. So what condition is it? The condition depends on the input. Okay, so B1, B2, B3 is the input. Depending on the input, you have one condition. So if B1, B2, B3 are equal to 0, 0, 0, then the condition is simple. It simply says that M odd, so the parity of the bit with odd index, is equal to 0. Okay, so you have to output, you have to sample from the uniform distribution over all binary strings satisfying this constraint. And if B1, B2, B3 is this, the condition is a little bit different. And here another condition, here another condition. So you have this problem. And so quantumly, you can solve it in 2 rounds. And the second claim is that in the local model, any classical algorithm that samples, or even approximately samples from the same distribution, require n over 6 rounds. So you get the separation I claim. 2 in the quantum setting, 2 rounds, and n over 6 rounds in the classical setting. Okay? So now I will give more details. So what is this quantum algorithm? So this quantum algorithm is very easy to describe. The nodes, all the nodes together prepare the graph state corresponding to the whole triangle. And then each node performs a measurement. So each non-corner node will measure its qubit in the x basis. This gives you a 1-bit outcome and will output this 1-bit outcome. So each corner node will measure it in the x basis if its input bit is 0, or otherwise in the y basis. Okay, and will output the measurement outcome. And you can do the analysis, and you will see that the output is exactly this. What you get is a sample from the uniform distribution satisfying this condition. And the same process really has already been studied in the prior work I mentioned. Our main contribution here is to show that you can construct the graph state in 2 rounds in the local model in quantum distributed computing. So I will explain this in a few minutes. Before this, I would like to discuss the classical lower bound. It's very easy to show. The proof is, again, essentially the same as in that prior work. So let's consider a classical algorithm that uses strictly less than n over 6 rounds. Okay, let's look at MR. MR is the sum of the parity of the bits on the right side with even index. So the first observation is that this parity cannot depend on B3. Why? Because B3 is very far from this side. So if you have only n over 6 rounds, the information of B3 cannot reach a node here. The first thing. The second thing is that you cannot have a product B1 times B2 because the information about B1 and B2 cannot be gathered at one of the nodes because the length here is n over 3 and you have only n over 6 rounds. So this means that MR should be an affine function of B1 and B2. And similarly, B2 should be an affine function of B2 and B3. ML should be an affine function of B1 and B3. And M odd should be an affine function of the 3 bits. Okay? So in order to solve the problem, you need to show that there exists affine functions like this that satisfy all these conditions. It's easy to check. You write a system of linear equations and you try to find a solution. But if you do this, you will see that there is no such solution. So it's impossible to satisfy all this condition if you use less than n over 6 rounds. So this finishes the proof of the lower bound. Okay? So this gives us our separation. So now, preparing the graph state. I will we need to do it on the triangle. Okay? We need to prepare the graph state corresponding to the triangle, but actually the construction I will present works for any possible network. So what is a graph state? You all know this. A graph state corresponding to a graph, G, is a state obtained by preparing 1 qubit in the plus state and then applying a Ctrl-Z operation for each edge of the graph. So for example, here you have 6 nodes, so you prepare 6 qubits, you apply an Hadamard gate, so you get the plus state, and then you have 7 edges. So you apply 7 Ctrl-Z operations. So for example, this edge corresponds to this Ctrl-Z operation, this edge corresponds to this one. Okay? So now we want to do this construction in a distributed setting. So let's consider this network. Each node will first prepare one qubit in the plus state. Okay? So the red qubit here. And then each node will prepare one ancilla qubit initialized to 0 for each edge. So this will give you this. So for example, this node here has 3 outgoing edges, so it will prepare 3 ancillas. And then, since we need to prepare the graph state, you will need to apply a Control Z operation on each edge. And this is done by using the ancillas and using 2 rounds of communication. So I will explain how to do this for implementing the implementation for this edge. Okay, so you first apply CNOT operation here and here. This can be done locally, okay, without communication. Then you will exchange the 2 ancillas. This will require 1 round of communication. Okay, so we exchange the 2 ancillas. Then you can apply the Control S operation. Control S operation is this thing. The point is that if you apply it twice, then you get the Control Z. And then you send back the ancillas. So this is the second round of communication. Okay? And at the end, you apply the CNOT again, and you can see that the ancillas are back to the original ket0 states. And on the red, for the red qubit, you have the Control Z operation that has been applied. So you get exactly what you wish to obtain. And of course, you need to do this for any edge of the graph. But the point is that all these processes commute. So you can apply this in parallel, and you need only 2 rounds. Okay, a few remarks. So actually, our quantum algorithm uses very short messages, only 1 qubit. So we get a stronger separation. We get the separation between the quantum congest model and the classical local model. So it's stronger than what's written here. The second thing, so this is a sampling problem. The output, you have essentially to simulate the outcome distribution of a measurement of a graph state. If you don't like a sampling problem, it's easy to convert it into a separation for a relation. So a relation is like a function, but you have many possible outputs. Another thing, here, this is a sampling problem, but a sampling depending on the input. So you have input bit B1, B2, B3, and depending of the value of the 3 bits, you have to sample a specific distribution. You can actually obtain a similar separation for a sampling problem without any input. Okay? The trick is simply to choose B1, B2, B3 at random. Okay? In that case, proving the classical lower bound is a little bit more difficult, but this can be done. Okay, so we did it in our paper. Okay, so, you get a similar separation even for a sampling problem without any input. So let me conclude. So prior works showed that in the congest model, quantum distributed algorithm can be more powerful than classical distributed algorithm, especially for the computation of the diameter of the network. So in this work, we show that in the local model, quantum distributed algorithm can also be faster. Okay? And the problem we considered is simulating the outcome distribution of a one-shot measurement of a graph state corresponding to the network. We show that you can do it quantumly in 2 rounds, because in 2 rounds you can construct the graph state. And we show that classically you need a linear number of rounds. So research directions. So first, this thing does not look very useful. It's an example showing the superiority of quantum distributed algorithm in a local model, but it does not seem to be very useful. So an important research direction would be to try to find useful applications of quantum distributed algorithm in the local model. And the next thing will be to prove the superiority of quantum distributed algorithm in other models. So we did it for the congest model, the local model, but there are other models. And I would like to make a short announcement of a recent result by me and my colleague Taisuke Izumi. We've shown that in the congest clique model, so congest clique model is another model intermediate between congest and local. You can design quantum algorithms for the all-pair shortest path problem working in complexity n to the 1 over 4, while classically the best known is n to the 1 over 3. So this shows the superiority, at least with respect to the best known classical algorithm in this congest clique model. And the nice thing is that this is for a very important problem in distributed computing, the computation of the all-pair shortest path problems. Okay, thank you.
Questions for the speaker?
Hi. You don't really seem to be using the unbounded communication capability of the local model here.
Yeah.
Is there maybe some better separation we can hope for by using more quantum communication than just 1 qubit?
Yeah, so you're right. So what our separation is really use only 1 qubit in each message. Yeah. So, but the point is that it's difficult to do better than this because classically you can do everything with n rounds because n rounds, n is the diameter of the network, so you can accumulate all the information at 1 round and do the local computation there. So you get this separation if you look at the number of rounds, 2 versus n is essentially the best that you can do. So maybe allowing more quantum communication can give you something, some advantages, but not really in the number of rounds, because it's already almost optimal with this separation.
Can I ask a quick clarifying question on one of the remarks you made? You said, oh, B1, B2, B3 are sampled uniformly at random.
Yes.
So they're part of the output?
Yes, of course, yes.
Okay.
Yes, there's a point. You need to make them part of the output, yes.
Okay. And so just one question about this. So the output there is distributed, right? And in order to determine, I mean, the condition on the output is, if you were to check that condition or something, you'd have to communicate a lot. So,
yes.
So can you get similar separations when just one node says something? Like, for example, similar as large separation?
I don't think so. We can show that at least if you consider functions, you cannot get any advantage in that model.
Okay.
So
I guess it could still be a relation.
Yes, so for relation, indeed, we don't know how to verify our relation here. Yeah. So, but it's maybe possible to find it, but we weren't able to do it. Yeah, it's an open problem. Yes.
Maybe one more question, if there's one more question. No more questions. Okay, thanks. Jean-François.